Solutions to assignment questions. This is a simple application of Snell's law. A light ray travels from air to medium X, as in the diagram. When you apply Snell's law, you should substitute the sine value of the incident angle, which is the angle in air, as the numerator, and then the sine value of the refracted angle as the denominator, as shown below. And don't forget to find the value of eta, x, and y in these equations. In this question, the light ray travels from medium X to air, and in this way, the refracted angle is the bigger one. When you apply the Snell's law, you should substitute the sine value of the bigger angle, in this case the refracted angle, as the numerator. And then for the sine value of the refracted angle, in this case, which is the smaller angle, put it as the denominator. And then you may find the correct value of the refractive index, eta. Similarly, you may complete part B and part C as shown below. And let me remind you, if you are doing corrections, you should copy the diagram and finish the calculations below. In this question, there are three layers: air, glass, and air again. The light ray will travel this way. First of all, there is a first refraction when light ray enter glass from air. So you may apply Snell's law in this way. We know that the angle in air is always the biggest. So we put it here, the sine value of the angle in air as numerator. And in this way, you may find the angle x. The light ray will then travel this way, because there is a second refraction. And then the incident angle will be the same as x. And what about the refracted angle in this way? 60 degrees, same as the incident angle in the first refraction. Now, what about if there are three layers of different materials? Water, air, and then glass. There is a first refraction here between water and air, and as there is a layer of air, it's easy to substitute the Snell's law, because we should always put the sine value of the angle in air as the numerator. In this way, you may find the refracted angle x. Then the refracted angle will become an incident angle in the second refraction. And this is actually 54.97 degrees. We put it here as the numerator, and then you may find the refracted angle in glass, which is y. Now, what if the thickness of the air changes? From the calculation of the last question, we can see we do not consider the thickness of the air layer, and so it does not affect the refracted angle in glass. In fact, if you look at the two equations above, and then you may combine them together into one, which look like this. And we are going to apply this equation for the next questions. In this question, there's no layer of air, there's only water and glass, and still you can find the refracted angle x by using the equation like this. The product of the refractive index of the layer and the sine value of the angle in the layer would be a constant. For those who are doing corrections, don't forget to use your calculator to find the value of the refracted angle x. This is a similar question without a layer of air, and still you can find the refracted angle y similarly. Now, what if there are more layers? You can set up a similar equation, and for each layer, it gives the same constant 0.86725. And if you want to find the angle z, you may just look at the very last part of the equation, and you may find it directly. This is your second lesson on refraction. Last time you have done the Snell's law experiment, and you have learned how to do calculations using the Snell's law. And this time you will see different applications of refraction. There are 4 different sections in this lesson. Number 1, image formation due to refraction. Number 2, the calculation of speed of light in different medium. Number 3, the refraction by rectangular block and prism. And lastly, number 4, dispersion of light. So here we go. We start from page 35. Due to refraction, there is image formation. Before we talk about image formation, let's see what happens to light when it travels from air to glass. You will see that it bends towards normal. What I mean is, the angle in glass is smaller. When we have air and glass, and light ray travels from air to glass, you will see when you draw a normal, then the refracted angle in glass is smaller. We say the light ray bends towards normal. And this can be important if we want to explain the following picture. The picture looks funny because the body of this man moves to the right. But why? Let's draw a ray diagram and explain what happened. Now we draw a ray diagram of this level, that is W, X, Y, Z. And you can see this light ray that comes from his body, which refracts and bends away from normal. And then we can see there is a virtual rays that points backward. Similarly, we may draw another light ray, which also bends away from normal. And then we produce it backward to find the image position. You can see that the image is on the right. And that's why the body of this man moves to the right, because his body is under water. And let's do it again. In top view, light travels in water and bends away when it goes into air. Produce the refracted ray backwards. Do it again. Produce the refracted ray backward. So you may locate the image which is on the right. There are many similar examples such as these. A fish in water or a corn at the bottom of water. So for the situation like this, when the observer observes the fish underwater, we may draw a diagram which is a side view. We draw light rays from the object that goes into air but bend away from normal. We draw another light rays, it also bend away from the normal. We produce the refracted rays backward. In this way, then you may mark the position of the image, and you can see the image is a little bit higher in position than the object. And you should note that where you see the fish is not actually there. And the other example is a cone at the bottom of a cup. Let's draw a ray diagram to illustrate the idea. We have a cup, we have a cone at the bottom. There's an observer, but at that time the observer just cannot see the cone. What we do is add water. When we add water, then the light ray will go this way. It bends away from normal so that the light rays go into the observer eye. And that means the observer can see the cone now. The another example is a stick that partially dipped in water. It appears bent. Why? You can see the ray diagram at the bottom of the page, and this ray diagram is almost the same as the one on the last page. What you have to do is to draw two light rays from the end of the object, and these light rays bend away from normal when they are reflected on the water surface. In this way, you may draw virtual rays to find the image. So after you have found the image of the red dot, which we mark it blue, then you may draw the image of the whole part underwater in this way. In nature, an archerfish produces a water jet to hit the bugs above water. However, if the archerfish found a bug at that position, due to the reflection of light, the image of the bug will appear here. So the fish will miss the target. On the other hand, if a fish target at a bug directly above it, there will be no reflection of light, so there is no change in direction. Similarly, a great blue heron also have the same problem, and that's why it usually targets at its dinner by looking normally to the waters. And now let's move on to the second part, refraction and the speed of light. The refractive index is indeed a ratio of the speed of light in vacuum and the speed of light in that medium. Simply speaking, when the refractive index is higher, when this number is larger, then the light speed in that medium would be lower. Well, how to use that formula? Let me show you how to find the speed of light in water. We have the refractive index of water to be 1.333, and that equals the speed of light in vacuum, which is 3 times 10 to the power 8, over the speed of light in water, which is V here. And using your calculator, you can easily find it to be 2.25 times 10 to the power 8 meter per second. 3.5. Refraction by rectangular block and prism. From question 35, we know that when light passes from air to glass and back to air, due to the two refractions, the imaginary ray will be parallel to the incident light ray. But the light ray is displaced laterally, and we say the light ray has a lateral displacement. And that lateral displacement is not always the same. It depends on the angle of incidence, the refractive index, and thickness of the block. Similarly, there are also two refractions when light ray travels through a prism. But you can see the light ray always deflects towards the base of the prism. And for the two refractions, there are changes in direction of light ray. First, by the angle d1, and then by the angle d2, so that altogether, the total angle of deflection is d1 plus d2. You may notice that white light is separated into rainbow colors when it passes through a prism. This is called dispersion of light. The reason of this is because different colors travels at different speeds in glass. That means they have different refractive index. Indeed, they refracted differently. You can see that red light deflects less and violet light deflects more. So the refractive index of violet is larger. It travels slower.